Assalamualaikum. Morning. Can you hear me? All right. Okay. That's good. Okay. I'm still approving participants now. Semua dah breakfast? Okay. So ni last esok insyaAllah kita akan mula berpuasa. Okay, so let us get started. I'll share with you the contents that will continue for today. CD-ROM, where's CD-ROM? Hold on, yeah. I cannot approve from the page where I share my content. I need to go out. Right. Okay. Let's get to the page. Chat box. Okay. Right. Okay. So let's continue from where we left yesterday. So we stop at this page. Right, we stop at this page where we discuss about introduction to a diode equation. So in order for you to calculate the total current that we've discussed yesterday, which is made up of minority carrier currents due to electrons and minority carrier currents due to hole, JE and JH. So you have to sum both of them to be able to know the total current, right? So and the total current is given by the above equation in this slide. You can see the slide, right? Is it visible? All right, okay, that's good. So total current is given by electron current plus hole current, and these two components are minority carrier currents. Okay, minority carrier currents. So these two, JE and JH. Okay, and that's given by, if you sum both of them and you summarize both of them, they can be summarized as J equal to J naught times exponential of QV over KT minus 1, right? So yesterday we have discussed that this J naught here is leakage current or saturation current density, right? So we want the J naught to be as low as possible to be able to get a high current in your semiconductor device. Okay, and right, so this is also called diode equation. So to be able for you to calculate the J naught, you have to revisit the previous page. J naught is equal to Q times D over L NS squared over NA plus another component from whole, right? And we want the J naught to be as small as possible, typically in the region of minus 12, minus 13 ampere. Okay, so in order for you to get a low J naught in your semiconductor device, you can actually design your device with the best parameters, with the optimum parameters. So in this case, to be able to minimize J naught, you can design your device by having large doping levels, large diffusion lengths. What else? Yeah, so that means you need to have large NA, large ND if possible. But trying to also show that you can get a large diffusion length, and this is a bit contradictory, because if you go to if you increase your doping level to a high level, last time we've discussed that it will lead to reduced diffusion length, right? So if you still can recall this curve, if you plot LE or LH, LE is the diffusion length, or LH, and if you plot against NA or ND, so you have like that trend, like that reducing trend at higher doping levels. So it's moving, so yeah, more or less like that. So larger doping levels or higher doping levels will lead to reduced diffusion length. So this is a bit contradictory. So that's why when you fabricate your device, you actually have to know your actual diffusion length, right? Yeah, you can also use materials with a large band gap if you can, but if you can't, then you are pretty much stuck with the same band gap. So J naught is the most important diode parameter. Okay, we'll see a little bit later on on PVCD-ROM. I'll go to that shortly. Okay, so this page is actually the summary of what we've learned so far. So it's more or less the movement or the transport of electrons and holes through the PN junction and also through quasi-neutral region. So if we look at the majority carriers, that means the carriers that that form the device, that form the material on P side or N side. Okay, so if you have a P type on the left, so that means your majority is hole. So if N type on the right, so majority is electron. Right, so in the bark, most of the currents drift as there are no gradients in the concentration. If you're talking about one bark, so you are not talking about any concentration gradient, because there's no gradient to begin with. So as the majority carriers approach the junction, the carrier concentration change, and we get a combination of drift and diffusion. Right, so let's recall, why do we have drift and diffusion near the junction? Right, why do we have drift near the junction? Kenapa kita ada drift dekat junction? Anyone? Um, let's look for a name. Wan Nurul Syafika. Saya tak pernah panggil Wan Nurul Syafika. So Syafika, any idea? Why do we have drift near the junction? Hello, Syafika? Yes. Okay, Syafika, kenapa kita ada drift near the junction? Yeah, you may talk or you might want to write. Up to you. Alright, you don't know. Okay. So anyone else? Siapa nak membantu? Yeah, Asriza, electric field. Yes, because we have electric field. So to know this answer, you have to go back to the definition of drift and diffusion, right? So you still remember, right? Why do we have drift? Because we have electric field. So do we have electric field in the junction? We have, right? So do we have electric field in the quasi-neutral region? No, right? So we don't have electric field in the quasi-neutral region, but we do have electric field near the junction or within depletion region, right? So that's why the moment your majority carriers approaching the PN junction, they will be affected by the electric field near the junction or within the junction, if you like. So last time we have discussed that as they approach the junction, the carriers will be swept by the electric field into the respective region. Okay, so right. Then why do we have diffusion near the junction? Anyone? Kenapa kita ada diffusion near the junction? Let's recap. This one is quite straightforward, right? Yeah, gradient of what? Yes, concentration gradient. Good. So we have concentration gradient near the junction. So do we have concentration gradient in quasi-neutral region? Do you have any gradient in quasi-neutral region? Anyone? Amirah, Nurul Amirah. Kita ada tak gradient, concentration gradient? No, right? Okay, thank you. So we don't have any concentration gradient in quasi-neutral region because after all, it's only one carriers. So yeah, you may argue that we have majority and minority, but concentration of minority is just too small. So if you're talking about 1016, so your minority carriers will be 10 to the 4. So that's not enough to affect the gradient, right? That's not strong enough. Okay, so let's continue. Drift will dominate for majority carriers. Note that electric field in the neutral region cannot be zero. Yes, in principle, if you want to summarize by equation, you can say that it's zero, but practically it's not completely zero in actual devices because you do have some effect as well in the actual device. But in theory, we assume that the quasi-neutral region is zero based on the plot last time that we discussed. Okay. Okay. So now let's go on to the next page before we talk about diode equation. So minority carrier concentration parameter. This is given by D over L or S recombination velocity has the dimension of velocity that can be considered a Bach recombination velocity. All this while we've been talking about surface recombination velocity, but we do also have Bach recombination velocity, right? you do also have bulk recombination velocity, but it's not that dominant when you talk about the bulk effects, right? As compared to the surface, right? We'll see why later on. So assume infinitely thick, uniformly doped region. Hold on, let me approve your friend here. Right. For good quality silicon, so if you're talking about silicon, the value of D over L, or also equal to S, bulk recombination velocity, is typically in the region of 300 to 600 centimeter per second, regardless of doping level and type. So let's recall, do we want our recombination velocity to be high or low? Last time we discussed about SRV, right? Surface recombination velocity. Do we want it to be high or do we want it to be low? Right? Yes, we want the recombination velocity to be low. So, um, so the same goes to bulk. So we want the SRV, surface recombination velocity, for the surface to be low. So the same goes to bulk. So we also want the recombination velocity for the bulk. It's okay, Azri. So we want it to be low. So same goes to the bulk. So we also want the recombination velocity of the carriers to be low in the bulk as well, right? So we'll look at diode equation. So this one assume forward bias voltages, right? So we'll see later on that the whole diode equation is also true in the reverse bias. So we'll see the diode equation for the positive side, which is forward bias, and also the negative side, which is reverse bias. Okay, so let's go to the next page. Okay, so if you if you plot the equation that we just obtained, this is diode equation, right? So if you plot this, so you're gonna get a curve like this, okay? So J is equal to J naught times exponential QV over KT minus 1. And you can now see the forward bias is on the right hand side, forward bias, and reverse bias on the left hand side. So you can see the curve changes exponentially on the right, but it barely changed on the left. But on the left, you can see a small value of negative J naught, if you like. This one, if you zoom in, later on you'll see there is a small value in the negative region of x-axis where it equals to J naught. So dia ada negative value kat sini ya. Bawah zero ni dia ada negative. So it's actually negative. It's lower side. So on the lower side, right? So for diode IV characteristic in the dark, this is also called diode equation. So diode is a rectifier. Have you learned about rectifier before in electronics? Ada belajar ke? So it's okay, Shin. It's alright, you baru habis test ah. Okay. So what is a rectifier? What is a rectifier? Apa maksud rectifier? So let's recall. What is a rectifier? Not the definition. What do you remember about rectifier? What do you understand about rectifier? AC into DC, all right, okay. So AC and DC, right? So it converts AC into DC, right? So AC means the device is allowing the current to flow in both directions, and DC in this case, as a rectifier, it only allows the current to flow in one direction, isn't it? Right? So if you look at this graph, does it allow the current to flow in both directions or only in single direction? Cuba tengok curve yang kita tengah discuss sekarang. Does it allow the current to flow in both directions or just in single direction? It's IV curve, by the way. So it's IV or JV. Some people call it JV because it's current density, so therefore it's J instead of I. But You can also put it as IV, sama aja. So it's just that the I doesn't have the centimeter squared below the ampere, but the J does have centimeter squared. Right, okay, just mean one direction, right? So yeah, this curve only allows the current to flow in one direction, because if you see on the right, on the forward bias region, so as you increase the voltage, the current increases exponentially, right? So what happens if you reduce the voltage to the negative side? If you give the voltage to the negative region, if you bias the voltage into the negative region, there's no current flow at all, right? So that means the diode, the PN junction, doesn't allow the current to flow in the negative direction, right? So diode is then a rectifier because it only allows the current to flow through one direction. However, we notice that we do have J naught, a very small value of J naught, which is typically in the region of 10 to the 12, 10 to minus 12 or minus 13 ampere per cm squared, which is very, very small. So, and this is called leakage current or saturation current density, something that you don't want to have in your device, but we have no choice. We will have it, right? It's just that when you design your semiconductor device or when you fabricate your device, you should be able to make sure that your J naught is small enough and it doesn't affect your current voltage performance, right? So for good silicon diode, J naught is theoretically in the range of 10 minus 10 minus 10 minus 13. This is considered very small. So if you have, for example, your current, your J naught is up to 10 minus 5 minus 6, that means your device has a very high leakage, right? So if you look at negative region now, reverse bias is as you increase your V to negative infinite, that means you're going to the left, you're going to high voltage on the left hand side, reverse bias. Look at the equation, exponential term in the diode equation, this one will become exponential of high negative. So that means the exponential component will be 0. So that means J, if your exponential component is equal to 0, so J will be approximately equal to negative J naught. Negative J naught. So J naught times minus 1 will be negative J naught. So that's why you have, as you go to negative region, negative voltage, negative bias, you will have this negative J naught. This negative J naught is actually here, as what you can see on the graph, right? So is it okay so far? Can you understand the diode equation from this slide? Right, that's good. So the diode only allows the current to flow in one direction. Therefore, the diode is called a rectifier. The diode doesn't allow the current to flow in the negative direction because it's a rectifier. So, however, we do have a small value of J naught due to the diode law equation, right? So it's very small in the region of minus 10, minus 12. So before we move to the next slide, let's look at PV CD-ROM. Let me share with you the page. All right, so can you see the page now before we move on? All right, that's good. So you can check this out in section 3.5. You can check in section 3.5 diode equation, right? I show you diode equation, section 3.5 PN junction and the diode equation. You can go up and see a little bit of explanation of diode equation from the top until down here. You can in fact animate your curve. So let's revisit again. So the diode equation says that I is equal to I naught, or it's actually J is equal to J naught times the exponential of QV over KT over minus 1. So see the explanation here. Number 2, I naught is related to recombination and thus inversely related to material quality, right? So at this point we haven't learned anything about the material quality yet. Um, you're going to learn a lot more in fabrication later on, ZAT387 next semester. So if you're from applied, in actual fabrication, if you're fabricating a transistor, for example, um, the junction quality, the PN junction quality will be very crucial, will be very important. So you really want to monitor the value of your I naught. You want the value to be as low as possible. And if your value is really low, so that means say in the region of 10 minus 12 minus 13, so that means your recombination is there, but it's really low and doesn't affect the performance of your diode or your transistor. However, if you fabricate your device, so that means fabrication here means you're doing multiple processes, sputtering, lithography, etching, implantation, diffusion, thin film metal, dielectric, interconnect, all those stuff until you get a transistor to be functional. Uh, there'll be points where there'll be uh, platforms for recombinations to happen. It's just that how do you control and how do you suppress all the recombination mechanisms in your device? So somehow your device will be affected by I naught or J naught, right? Because recombination is there. So this will explain about your material quality. So for example, if you have a device with I naught or J naught, if you like, with J naught of 10 minus 12, and the other device with J naught of 10 minus 5, so that means device your device with J naught of 10 minus 12 has better material quality compared to 10 minus 5. Okay, so therefore it's an indicator of material quality. So non-ideal diode include an huruf N term in the denominator of the exponent. N is the ideality factor ranging from, hold on, I need to move this, ranging from 1 to 2, that increases with decreasing current. Okay, so yang kita tengok sekarang ni is an ideal diode equation. So that means you don't see any N here, right? You don't see any N. So however, when you talk about non-ideal diode equation, you will have N. I'll show you later on. Let me just show you. All right, if you look at non-ideal diode here, below here, you can see the exponential component also has N factor, ideality factor. So it typically ranges between 1 to 2, depending on the material quality, right? But if you talk about ideal diode equation, there is no N factor. So you assume everything to be perfect. But if you're talking about experimental diode that you just fabricated, for example, you will see the value of N is not 1 because it's not perfect. So your junction is not perfect, right? Okay, so let me show a few more things here. So look at this ideal diode equation. I is the net current flowing through the diode. I naught or J naught, if you like, is the dark saturation current, also called leakage current density in absence of light. You can actually determine this by when you, let's say if you fabricate a diode or a transistor. A diode is the simplest form because it's just a PN junction. While if you talk about transistor, it's a NPN or PNP. It's more than one junctions already. So say if you get your PN junction ready, then you want to measure your IV curve, you can actually measure your IV curve in the absence of light. So that means you just measure your IV curve in a black box. Dalam kotak hitam, there's no light at all. You just put the probe on the negative side, put the probe on the positive side, and then you bias the voltage to the plus side and bias the voltage to the negative side, and then you can actually get the dark saturation current, right? So therefore it's called dark saturation current because it's measured in the dark, no light. Okay, voltage, V is the voltage applied across the terminal of the diode. So across your plus terminal and negative terminal. Q Q is the electron charge, K is the Boltzmann constant, and T is the temperature. So look at this. I naught diode saturation current is an extremely important parameter which differentiates one diode from another diode, and also a measure of recombination in the device. As I said later on, if you're comparing 10 minus 12 versus 10 minus 5, of course 10 minus 12 has a better material quality, right? A diode with a larger recombination will have larger I naught, just like my examples now. So larger I naught, more recombination. Smaller I naught, smaller recombination. So if you look at this equation, you can also notice that I naught increases as T increases. So if you have your diode, you say you put your diode to measure IV curve, and then at the same time you heat up the plate. For example, you heat up the temperature to, instead of 300 Kelvin, you go to perhaps 1000 Kelvin. So you will notice that your I naught increases. So that means your leakage increases. So why do you think when you increase the current, your I naught increases? Kenapa bila kita increase current, I naught increases? Any idea? Why higher temperature leads to higher leakage? Anyone? No idea? Oh, 11:36 dah, so fast. Okay, I'll leave it to you to find, okay? I'll leave it to you to find. Cari kenapa I naught higher when T is higher, right? So I naught decreases as material quality increases. So if you have a good material, better material, you have lower recombination. It makes sense, right? If you're talking about chocolate red hall recombination, for example, if you have a better materials, that means your defects should be less. That's why your materials are better. So lesser defects means lesser recombination, especially SRH. So therefore you will have higher lower I naught. Sorry. Right, at 300 Kelvin, KT over Q is equal to 26 millivolt. This is called thermal voltage. We have discussed before. So just now was all ideal diode equation. So now let's look at non-ideal diodes. Ideal diode can only be achieved in theory. So if you're doing your own fabrication, you will not achieve ideal diode equation. There will always be the n component in your equation. That means you're gonna have your ideality factor. It's not 1 anymore. So in the ideal diode equation, n is actually equal to 1. So therefore, it doesn't show up. You don't see the figure 1, right? Because it times 1 anyway. So in the actual diode that you fabricated, it may be 1 plus, it may be 2 plus, it may be 3 plus, depending on the severity of your diode, right? All right, so you can later on, you can come down here to the curve, and you can let me just show you one example. Okay, you can come down here and play with the dark saturation current density. I naught here, you can go to the right to get higher leakage current, right? Going to 10 minus 10. You can also go to the left to go to lower leakage current, or minus 13, minus 14. And you can see the shape of the curve changes accordingly, right? So you can see that. You can also play with what's here. You can also look at the temperature. So if you go towards high temperature, for example, now it's 300 Kelvin. If you go towards high temperature, you can see how the curve changes, and you can also go to the low temperature to see how the curve changes, right? All right, so that equation. Let me finish a couple more slides on the PowerPoint. All right, can you confirm? Can you see the slide now? All right, that's good. Okay, so how many more do I have? By junction. Okay, we may have to continue tomorrow, but I'll go through one or two. All right, so all this while we have discussed, I think yesterday, right? Yesterday we've discussed about thick diode and thin diode, right? Just a brief explanation of thick diode and thin diode. So yeah, let's recall what is thick diode. What is thick diode? When do you have thick diode? Yeah, that. Thick PN junction, yes. Okay, what is the other indicator? What about carrier recombination? Diffusion length, yes, exactly. Good, Jasmine. Diffusion length of your carriers is less than the diode thickness or your device thickness. So that means if your diffusion length is less than the device thickness of your diode or your diode thickness, that means the carriers are going to recombine before they reach the contact. Maksudnya dia jalan halfway, gone, recombine, then they don't make it to the contact, right? So therefore, it's called thick diode. On the other hand, we also have another diode which is called thin diode, right? Thin diode. So if thick diode is as defined by Jasmine, so what is thin diode then? Apa maksud thin diode then? It's just the opposite, right? Yes, it's just the opposite. Diffusion length more than device thickness. So maksudnya the carriers can now diffuse, can now move through the device until they reach the contact without having recombination. Means they can survive their journey. Maknanya dia nak pergi dia letak minyak Penang ke KL, memang minyak tu cukup lah sampai ke KL lah. Dia letak sampai dekat Slim River je, then thick diode. Then kalau sampai ke KL memang thin diode. Dia sampai ke destination, right? So that's the simplest version of the definition. Let me show you something. Right. Right. Can you see the whiteboard now? Okay, that's good. All right. So let me draw to you the thick diode and thin diode to illustrate so that you can understand better. All right. This is an example of a thick diode. So for example, this one is your silicon. So the whole thickness is perhaps 300 micron. So this is for thick diode. Thick diode. So if you have a carrier, say this is your junction, for example, So katalah ni N-type ke atas, P-type kat bawah. So if you're talking about minority carriers, so if they katalah you apply the bias and then your electrons from the N-type can now diffuse again, sebab barrier height dah reduce, can now diffuse crossing the PN junction into the P-type, and then in this P-type, the electron will become minority carrier or majority carrier? Anyone? Is now a majority carrier or minority carrier? Electron in P-type. Minority carrier, right, Farah? Right, so it now becomes, yes, good, Helena. Minority carrier in P-type. Ni lah yang kita calculate itu kan, NPA and stuff, NP0, NPA, all the stuff. This is actually the illustration. So, kalau dalam device nanti, we're going to learn that you're going to have metal contact on top, metal contact at the back. So metal contact on the N side is for the negative contact because it sits on the negative on N-type region. So the rear contact is for positive region. So nanti kalau you nak connect dekat terminal, it has to be negative, it has to be positive here. Right? And it's also a forward bias here, right? Forward bias. Okay, forward bias. So you want this electron now, you want this electron to diffuse sampai ke metal contact ni. So that means kalau you punya junction ni, let's say the thickness is about 1 micron, so the electron has to diffuse another 299 micron to get to the real metal contact, right? So if if the electron doesn't make it to the contact, maksudnya dia akan recombine kat sini, dia mati kat sini. That means gone here. Electron is gone here, mati. So you will not get anything at the contact. You'll get 0. So nothing reaches the contact because the electrons have already recombined in the p-type region, and that's it. So in this case, it's considered as a thick diode. Okay. Sebab dia terlalu tebal, diffusion length is, so diffusion length of electron is less than thickness. So T is thickness here. Okay. So that's the first case. So the second case is that it's called a thin diode. Thin diode, the very same situation, except the thickness is very small. Katalah kat sini thickness dia is only 1 micron, and your junction is somewhere there inside. Say thickness maybe around 300 nano. So belakangnya ada lebih kurang 700 nano je dia nak go through. So then you also have your metal contact on top, on N side, metal contact at the back on P side. So the same electron here, kalau dia dapat diffuse kat sini, so the same electron will have to diffuse only around 700 nano. Okay, katalah kat sini dia punya Le is katalah dia mati kat sini tadi kan, so say 200 micron. So if the same electron has Le of 200 micron in this thin device, tapi dia punya device thickness is only 1 micron. So Le is more than T, right? So Le is more than T. So you now have a thin diode. Sebab carrier tu electron can diffuse a lot longer, but it only has to travel a short distance. So dia boleh pergi lagi jauh sebenarnya. So maknanya dia nak sampai ke contact ni senang-senang je, right? So the same goes to hole, right? Hole goes to the other side, sama je. So thick diode versus thin diode. So is it clear so far, thick diode versus thin diode, before you go to the equation? Is it okay from the illustration? Right, good. So the key thing here is the diffusion length against device thickness, right? So if the diffusion length is less than the thickness, it's called thick diode. If the diffusion length is more than the device thickness, it's called thin diode. Okay, that's good. Let's go back to the slide. Okay, you can now see the slide, right? Okay, so let's move on with the slide. Sekarang kita nak tengok what is the impact of surface recombination on J0 in thin diode. Remember, it's now a thin diode. Kita nak tengok the impact of surface recombination on J0 in thin diode, right? So kalau kita compare, let's go back to the example just now. Kalau you compare thick diode dengan thin diode, do you think the surface is going to be more dominant in the thick diode or in the thin diode? Rasa-rasa lah kalau based on logic. So we normally talk about bulk and surface in semiconductor devices. If you look at thick diode versus thin diode, do you think surface recombination is going to be more dominant in the thick diode or in the thin diode? Any guess? Thick diode, right? Ilana say thick diode. Azika, thin. Any other ideas? Oh, 9:50 dah. Let me go for another 5 more minutes perhaps. Alright, thick or thin? Let's get a vote. Thick, okay, too thick, thin, thick. Alright, right, thick. Okay, let me see which one do I see more thick. Right, let's have another 5. Thick. 4. Another 4, please. Yeah, just put anything thick. Alright, another 3, please. Thick wins now, thick wins. Alright, another 2. Right, and a thin. Okay, so that's thin. And now last one, please. Anyone? Now thick wins. Last one after Azrizal. Last one, please. Anyone? No closure. Right. Thick. Okay, the closure is thick. So thick wins, right? Thick wins. Okay, why do you say thick? Kalau you tengok dekat katalah you buat calculation matematik Katalah you buat calculation matematik. Kalau you kira surface area, that means let me put on this color. Okay, kalau you kira surface area of this thick diode, kira this, calculate this plus this plus this plus this, total jadi total area, and then you ambil this one plus this one against over total area, then you compare dengan thin diode, this plus this plus this plus this as your total, and then you ambil this plus this over total just now, over the whole thing. Yang mana lagi banyak? Yang mana lagi tinggi total area? Fraction of surface area. Sick? Really? Dia punya width of the device sama. Pak Ika, dah air tu. Alright, let's do some math here. So okay, now you answer again. Thick or thin? Thin then, yes. Isian thin then, right? So if you look at the surface area, tu cara mudah lah. Cara mudah yang nak kira whether or not the surface will impact the device. You need to base on the total area of the device. So that means, yes, the answer is thin diode. So if you go back to the slide, so if you want to examine the impact of surface recombination, which is due to the surface defects, so maksudnya you kena tengok surface tu banyak mana lah. Surface tu banyak mana out of the total area. So that means if you're comparing thick versus thin, kalau you tengok thin, you akan nampak pretty much the whole area of the thin diode is actually surface, right? Tapi kalau you compare with thick diode, just a fraction of the total area is surface. Tapi kalau you tengok a very thin slice of something, the whole surface is thin. The whole surface area is surface. You tengok kat depan, kalau you pegang duit shilling kan, dengan you pegang shilling yang banyak-banyak tu, so you banyak-banyak tu, dia punya device thickness is quite high. Kalau you ambil shilling 50 sen for example, you can see either head or tail, right? Head or tail. So that means pretty much the whole thing is surface. So that means that is one example on how do you see the impact of surface on thick versus thin diode. So therefore, to be able to examine the impact is higher, is more significant in thin diode. Therefore, to be able for you to calculate the J naught, right, in thin diode, tadi kita dah tengok, sebelum ni kita dah tengok calculation of J naught in thick diode. So you need to also factor in the GF or geometry factor. Okay? So GF is called geometry factors of electron and hole of the surface practically. So you have to factor in geometry factor in the calculation of J naught, while GF is given by this and this. You don't have to memorize this equation. Saya cuma nak tunjuk the impact of the geometry factor on the thin diode versus thick diode. Okay? So surface recombination is more significant in thin diode, but less significant on thin diode. Okay, let's go to another slide. Last one, then we're going to stop. Right, for the given doping level, assuming same doping level, the geometry factor, GF, is fully determined by the two ratios of S over S, S infinite over S, H over L. Two regimes, the two regimes can be distinguished as, right, H is the device thickness, H is more than 3L, ni more or less a more specific representation of your recombination tadi, right, in this case surface has no effect on the GF, hence also on the J naught. Ni untuk thick diode yang kat atas ni, right? The surface has strong influence on GF and second one, right? Note that for GF is up to 1. So in this case, the surface has better electronic quality than the bulk, and the diode's J naught can be reduced by thinning the diode. This is the reason. This is more towards solar cells actually. So kalau you nak improve you punya uh, J naught of the diode, one approach is to thin the diode, right? Make it thinner so that you can actually improve the voltage of the device. Okay. No need to worry about this S and HL. It's just an example for solar cell. All right. I'll stop now, and we still have a couple more slides actually. Yep. Okay. I'll just stop now. I want you to go back and try this example on page 29 and 30. 29 and 30. Same question, but A until E. So we're going to discuss this one tomorrow morning. Okay. So this is on PN junction, majority carriers calculation, minority carriers calculation, and also VBI calculation. Yeah, including the bias as well. Bias and yeah, positive bias and negative bias. Forward bias and reverse bias. Okay. Please go back and try, and we'll discuss tomorrow. We have class, right? Tomorrow's Friday. Yeah, we have a class tomorrow at 10. So yeah, maybe I'll call you up and you can share your answers to this, right? We'll do A to F, A to E, sorry, A to E. Then we'll move on to the rest of the slides for this topic. Okay then, that's all for today. Any questions? Stop sharing. Alright, no problem. Selamat berpuasa kepada semua. So esok puasa. Okay, selamat puasa semua. Alright, no question. Alright then, so I'll see you tomorrow. First Ramadan, insyaAllah. Alright then, stay safe. Bye bye. Ya, selamat tarawih kat rumah. Malam ni kena jadi imam sendiri ya. Tak ada imam jemputan. Okay, Assalamualaikum. Bye.